Okay, should be good now. Okay, so think about where we have gotten so far. We've looked at the performance improvements we've seen inside processor core. We've looked at a more modern multi-level and co-optimized memory system. And now we're going to break out of the late 20th century and finally get into the 21st here. Not because these things didn't exist before, but because they became ubiquitous by about 2005. Multiprocessors. Multiprocessors have been around for a long time. There used to be really entire companies whose business model was building all of the glue that took a bunch of separate processors together and making them a high-performance machine. Sun Microsystems back in the day, before they got bought up by Oracle, that was a big chunk of their business model. And HP used to do that as well. Okay. So definition, a multiprocessor is any computer system with at least 2 processors, right? This is not terribly complicated nomenclature, but we'll define it anyway. See if we can get this to go away. You want to go away? Do you? Probably not. Maybe? There we go. A multi-core is a specific type of multiprocessor. So again, multiprocessors are old. There were multiprocessors in the 1960s at IBM, just like everything else in the late 1960s at IBM. But there were not any multi-cores until quite a bit later. So the first real interesting proposal in research, you can go back and look in, I believe it's 1996, processor proposal called Hydra out of Stanford by Kunle's group. By the early 2000s, you could see research prototypes of things like the MIT RAW processor, which had 16 cores. The papers were coming out around 2001, and they actually fabbed the chip 2003. Commercially, you could go and start buying these things with a 2-core Pentium 4 in circa 2003. So around the turn of the century, broadly speaking, everything was not just a multiprocessor, everything was a multi-core. Right? So these were no longer specialty systems. Although interestingly, if you look at the fact that it's been 20 years, the programming models have advanced, but the degree of depth that we have with them perhaps has not. So we'll dwell on that broadly a little bit later. So here is one possible way that you could build a multiprocessor. You have a bunch of cores. You could all have them have caches. There could be some sort of interconnection network. Goes to memory, goes to I/O. This is what we'll be talking about in this slide deck. We'll be looking at a different topology in terms of how you could connect all your cores together in the next deck after this. As a shared memory machine. We'll define that in a second. So let me give you the good and the bad about multiprocessors versus all the things we've seen so far. All right, so everything we've seen so far, with the exception of VLIW, where you had to go and recompile it, was going to take your existing code, and the hardware was just going to make it faster. Right, so you take your existing binary, no work required, throw it onto a superscalar out-of-order machine. It gets a little wider, ROB gets a little bigger, you get a little more performance, life is beautiful. If I give you another core and you have a single-threaded program, you're not going to experience enormous benefits from that because your code only runs on one of those cores. Right, so this is a different model of scaling. It is a resource that if you exploit it can give you lots of benefits, but it is one where the application is going to have to get out and walk a little bit. Right, the hardware, or as again, VLIW hardware plus compiler, is not going to do all of this for you. Right. So in particular, the thing that multi-processing, the use of multiple cores, is going to very naturally give you is higher throughput, right? The peak instruction throughput of this machine, if I slap more cores on it, is going to go up. That's kind of natural. Right? If I can do 3 instructions per cycle here, and 3 instructions per cycle here, and 3 instructions per cycle here, it's delay for a bit what happens when they all try to talk on this at the same time, right? But the peak, at least, bandwidth of this machine is going up. But adding these additional cores does not make any one of them faster. Right? So the latency of any individual action is not going to be particularly improved by adding more parallel processing resources. Okay? Now, if your program has been restructured such that the computation itself is inherently parallel or concurrent, then the increase in throughput can improve the latency of your program. Right? If you have a parallel program running on a parallel computer, it's going to do better than a parallel program running on a uniprocessor. Right? Now, one of the things that you want to keep in the back of your head is we didn't just decide to do this because we thought parallel programming was amazing. For those of us who were around using computers in the middle of the 2003 to 8 sort of range, you switch over from a 1-core machine to a 2-core machine. There were some enormous benefits, many of which result from the fact that, again, you have an application and you have an operating system and all the other background processes. Having 2 cores lets your applications stay on 1 core and not get scheduled in and out. You're no longer time multiplexing all the resources of your machine, even when you're running one application. But we very then rapidly noticed that going from 2 to 4 and 4 to 8 and so didn't do much more, right? So that was a one-time boost. So the reason was not that this was going to be some magical enhancement with a lot of value proposition. It actually was that we didn't entirely understand what else we could do with our transistor resources. So by the early to mid 2000s, there were some challenges with Dennard scaling, right? So, we think about Moore's law. It's about increasing levels of integration, particularly thinking about it as increasing the number of transistors per chip. But Moore's law only works when the power efficiency of a transistor is also scaling. Otherwise, as you pack more and more and more components into that area, the thermal density is going to rise, and it did. Again, as I said before, physics just doesn't seem to like us very much, right? Physics is why we can't have nice things. So there's some fundamental power thermal constraints. Again, the constraints, let me clarify that a little bit. The power constraints are a function of the manifest in terms of the thermal constraints. So it's not that they couldn't build a chip that drew 500 watts. It's that they weren't in the refrigeration business. That wasn't a good margin, right? Their margin is turning, very subtly tainted sand into several $1,000 machines, right? Silicon is cheap. The impurities are not that expensive. It takes a few $1 billion to build your first one, but each additional chip is like $5, right? Refrigerators are a very different business model. Intel does not want to be in the refrigerator business. That is not the same sort of margin, not the same sort of scale up, right? So no. So they say, look, we're only going to cool this so much. If we only cool it so much, we can only power it so much. If we only power it so much, then there's only so much we can do, right? You can actually go a little further here and understand the time it took us to get where we were. There was a little bit of a misstep, right? So while the fundamental reason why we were having these power constraints was physics, transistor physics, CMOS physics specifically, there at least was a brief period where we thought, well, maybe we just built the wrong microarchitecture. And you can see this play out in terms of the lineage of the Intel cores, right? So there's a through line from the Pentium 2 to the 3 to the 4. And then we go from the Pentium 4 to the, again, I don't know what they were drinking in Hillsborough or Santa Clara at the marketing committee, but when they called it Intel Core, just to be maximally confusing, because all the other things were also cores. All right, they go to the core architecture, with their move to their proper multi-core. The Intel Core architecture actually came out of the mobile division, right? So I thought maybe the issue is we just have an inefficient microarchitecture. We shouldn't have been, we shouldn't have been trying so hard. We shouldn't be having our 50 pipeline, deep stage net burst architecture. That's going to fix our power problems. That's how we're going to scale. Life's going to be fine. No, the answer was it was still physics. Right. So they've actually basically rebooted themselves from a Pentium 3 that had gone on to the mobile division in Haifa, then came back to the main line with the Intel Core, Core 2, et cetera, architectures. Okay. So again, to contextualize all of this, this isn't a move to multi-core because this was going to be, the next awesome thing to make your programs faster. It was because this is what we knew how to build with more transistors. Because I don't increase my thermal density by stamping out more slightly less aggressive cores versus taking all of those transistors and making them into one even more aggressive core, right? So scaling the width of these structures increases your heat, right? Stamping out more of them, less so. Let's contextualize that. Now, that's, roughly 2003, 2005, 2008, depending on sort of which groups of people finally, saw the light. If you look at where we are in the last few years, this is a reasonable sample of things. You go out and you get a Genoa model EPIC processor for AMD, 96 cores, 192 threads, right? Also chiplet design, also 360 watts. Good luck with that. This is the Xeon Platinum 8490H, 60 cores, 120 threads, right? So you ever heard the multi-core, more than one, many-core? Where does multi-core become many-core? I don't know, but probably by the time it's 96, you can call it many-core architecture. 1, 2, 3, many, right? How we count. IBM actually has some different interesting points in this space. They have a pair of models of the Power 10, one the SMT4 model, one the SMT8. They both have 120 threads. They either have 15 or 30 cores, 8-way or 4-way SMT. So now the power numbers for this are a little funny because you never buy just one. So they say, no, actually, you look at the power numbers and they say 2 kilowatts, right? Because it's not just a multi-core, it's a multi-socket. But everything's multi-core, right? Long story short, everything that you have grown up with, right, with a couple exceptions for those of you who are closer to my age, class, everything you grew up with is a multi-core. So I'm talking about something where you didn't even realize there was another option, right? Okay. Now, they're also actually SoCs. So the other thing that we did figure out some other things to put on here other than just more cores. So here was a 2012 era chip. You can see the integrated graphics processor. Yes, we will talk about GPUs. We'll talk about GPUs after we talk about multiprocessors, since GPUs that are interesting are also multiprocessors. So bring that back together. So here was 4 cores by 2 threads each, plus a graphics processor, plus a memory system agent, plus. But there's a lot of other stuff out there other than cores that have been scaling. Moore's law integration does continue apace. But again, the complexity of each of these is the right way of looking at it is that the first thing that we are going to run out of to make this give you value is not going to be more transistors. We've got lots of transistors. We're going to run out of power thermal density management issues. So that is also why, if you go back and you see these pairs of numbers here, this is how fast it can run. This is how fast it can continue running without cooking itself. Right? All these boost clocks, that's Dennard scaling hating you. Right? This is physics. This is what the transistor can actually run at. Right? This is the capacity of the machine. This is the value proposition. This is, I can't do this without generating too much heat. Okay. So if I want to cobble together multiple processors, right? I have some questions I have to answer to make it a multiprocessor, right? If I have one computer over there, I have one computer over there, they're not connected to each other, it's not a multiprocessor. That's just two computers, right? So we're going to look at a couple of different answers to these questions, right? They are not singular. There is a design space. All right, so question one, how do they share data? Right, if they cannot share data, they're not really logically one machine. Right, there are a lot of options there. How are they going to coordinate? Right, coordinate, synchronize. How are they going to agree on anything? And a lot of this is really going to come down to questions of ordering. It will turn out to be important to understand whether something happened before something else. Very difficult to make useful computations and decisions if you've lost your notion of time, right? And then depending on your decisions to Q1 and Q2, how much can you realistically scale this before you have to start doing some different design options, right? Now, when we're looking at this, there's some entanglement with the programming model, but we're mostly going to be answering question 3 from a hardware perspective, right? So depending on how you do Q1 and Q2, different programming models are easier to express good ways of exploiting this hardware. They have their own scalability constraints. Take a parallel programming class if you want to fully dive into that, but we're not going to go into that in enormous depth. Okay, so we're going to start with shared memory multiprocessors, in part because if you buy a chip multiprocessor, all your chip multiprocessors, unless you're a weirdo who only buys like Xeon Phi and then tries to run your desktop on this $10,000 part for no particular reason, is a shared memory multiprocessor, right? Anything you're going down to the Best Buy and buying is a shared memory multiprocessor. Best Buy, Newegg, et cetera. Okay. So what we mean by shared memory is that there is a single physical address space, right? So the machine, all of the cores, the memory system can agree that physical address 5000 is some particular place in this system, right? There's only one of them, right? Obviously, in a multiprocessor model, there are going to be lots of virtual address 5000. We're not going to worry about that. We're talking about the physical address space of the machine. In a shared memory multiprocessor, since memory is shared, the coordination communication is going to happen through memory, right? Memory is the glue that binds all of these processors together. I am not going to be able to reach into your core and see register 5. That's not going to work. That's not the semantics, and it's not a physically interesting way to build the system. But if everyone has to be able to physically communicate bits on wires to memory, then logically there is a path from every core to every core through the memory. So we're going to synchronize through the memory, right? That is the common point that all of them are going through. Right? So you're going to need some sort of synchronization primitives to understand how to control the access to data, right? So things like locks, barriers. The hardware will provide you some support in how to implement these. Please note that the hardware does not actually, in any modern machine, do locks directly. There have been lots of proposals for that, but that's not what the ISAs actually do. They give you a primitive with which you can implement them, so do try to not get those too confused. And since we're going to be sharing all of this, this address space, we are going to keep our caches coherent. That's going to be a fair chunk of what these slides cover. How do we get all of these processors to agree on what the value of address 5000 is? That's the coherency problem. Okay. There are a couple different styles. We're not going to dwell on this too much. Just know that this really mostly plays into the scalability and how well you can exploit them with the same code. You can have a uniform memory access model, a non-uniform memory access model. It's a question of whether or not you have exposed the fact that in your multiprocessor, some portions of your memory system are physically closer to some of your cores than other portions of your memory system. Right? So that can be exploited. So we're going to first dive into this, right? Any questions on just what I've described in terms of Q1 and Q2 before we talk about how coherence works? Coherence is going to be a new thing. Don't worry, we're going to define it more, right? But basically, it's about being able to agree that address 5000 has a well-defined value. Right? Okay. So we do need a well-defined set of concurrency abstractions. I'm actually going to come back to this. Let me do coherence first and then come back. Okay. So let's describe the coherence problem. So the coherence problem arises because, as we just spent a couple of weeks on, caches are useful. You'd like to have them. You'd like to not be paying that enormously high cost of accessing memory every time you touch something. But if I have multiple cores with multiple caches, and let's say that there is some shared variable x, right? So core 1 is going to load x. X is currently 0, loads it from memory, now it's 0. Great. Core 2 is going to load x. Loads it from memory, now in its cache, there's another copy of x, it's 0. So far, so good. Core 1 stores to x. Houston, we might have a problem, right? So if we do nothing else, if we do only what we have described so far, I've got to write back cache. I don't need to write this back yet. I'm good. Right? All right, eventually write it back. No. Core 2 loads x, still 0. Right? This would be incoherence. This would be a disagreement in this system on what the value, again, x is somewhere in memory, right? Has some logical address. The caches are just cached copies, right? They should agree on what the value of x is. They do not, right? We're going to have to come up with some set of protocols to do this, right? So a coherent memory system, right, has the following property, right? And it's basically that you're going to have a set of stores to a single value, an address in memory, right? And that's going to determine what values could possibly be returned by a read. Okay? And what you're going to ask for coherence is that you have a serialization. Right? So if you have a bunch of stores to a particular location and then you do a read, right? The set of updates to that particular location must be mutually agreed on. So I am never going to get an ordering change with respect to 2 stores to the same location. Now, it might be that I get an older value. That's logically the same as my load having happened before that store happened. Right? That's okay. So coherence doesn't have to say that everyone immediately agrees on what the value is. Coherence is going to be that we agree on a logical time ordering of the evolution of a single value in the system. And if I get a value that is out of date, that is equivalent to being logically earlier in the system, right? And we have to have these caveats because it will turn out that some of these things will be in flight at the same time. Right? So if we go back to this example, right, if I have this update here, x is now 1, everyone agrees x is 1, and this still thinks x is 0, this is incoherent. If, however, during the process of this being written to 1, I ask this, I still have to have a well-defined answer, right? So it's still perfectly fine to be returning 0 while 1 is being written. It is just logically earlier, right? There will be a point in time at the system at which this x equals 1 will be agreed to have happened. Everything after that has to return 1, right? Everything before that was going to return 0. Things that are happening during that write, right, can either be sort of logically before or after that right internally. A little bit of nuance. But we'll look at the protocols, and at the granularity we're going to be looking at it, the ordering will be fairly clear. We're going to use a bus, we're going to synchronize, and you're either before or after the bus transaction. Now, coherence is a property of a single address in the machine, right? About agreeing on what value a read to a particular location could return, right? So the serialization of all the stores to the same location. So if I write A and then B and then C, right? Then I'm never gonna read a value, get C, then read a value and get B later, right? So those are nicely ordered. Consistency is going to turn out to be trickier. Consistency, well, technically determining when a written value will be returned by a read, that is the definition. You can logically think about the relative ordering of multiple different addresses in the machine. Right, so a coherent machine, which we'll go into quite a bit of detail on and look at protocols to implement, they're relatively straightforward, right, is going to get you agreement on what values some particular location A has. But if I want to understand when all of the cores will see something that happens to location A versus when they believe something happened to location B, the relative ordering of those two events, those are consistency models, and they get complex real fast. Right? You're looking at all of the potential orderings among multiple memory accesses to different locations, right? And that will turn out to be an ISA-determined feature. Your ISA will determine what your consistency model is. And then this will determine how you can or cannot build your machine. So there are going to be semantics here about what you can observe. We'll get to this later. We'll dig on coherence first. Interestingly, you can think about coherence also actually as the degenerate form of consistency of a coherence is a consistency model when you only have one memory location. But while that is true, it's not a terribly useful thing, in my opinion, to ponder. Okay, so I want caches. I want to have a notion of what a variable value actually is. Otherwise, it's kind of difficult to communicate in my shared memory machine between two of my cores, right? If I update value X and you never see my update to X, that's kind of useless. So how do I handle replication, right? And how do I handle the migration how do I handle the migration of these updated shared data items to the other participants in this protocol? Okay. Now, doing this right in your multiprocessor machine is kind of critical for performance, right? So how many people have ever looked at any distributed systems literature ever? Okay. Anyone ever heard of Paxos? No? Okay. So if you're looking at large-scale systems that have replication for failure tolerance and so forth, there are a whole bunch of protocols, in software to ensure that multiple copies of the data eventually, reach some common agreement on what happened, right? And that this is again for failure tolerance in these sorts of geo-distributed systems. So they're solving similar problems, but the scale that they're solving it for Facebook or for your bank is a very different time scale than you need to be solving it here. So some different properties are going to ensue. But these problems do actually turn out to be common. Okay. One other side note, I've kind of given up on Kahoot. I really miss clickers. I'm just an old dog who can't be taught new tricks, apparently. So I'm just going to go over some of these questions, even though we don't have the clickers, and you can ponder them for a second. And I'm just going to give everyone the Kahoot points because I don't know. I saw it a couple times. It looked cool. Didn't work out. It's fine. So think back to this slide here, slide 9. So there's another wrinkle, right? Storing and loading this variable X, right? Let's ponder this question too. So what if the variable x is promoted to be in a register rather than loaded and stored every time I'm reading and updating it. Is that going to be any worse, any better? I'm going to walk through these. Registers are not part of the memory system, right? Your registers are not in the same memory space. Your registers are not kept coherent. Anything that happens in your register is your problem, right? No one is going to tell you about someone else's update to register 3, right? Think about the bandwidth required, even if you want to do that, if it made any sense. Okay. Changes to memory will not backpropagate to registers. No, B is also false, right? There's not some magical system that understands what variables you have in play and then goes and pings you when someone changes them, right? It's not some notification system that your subscribed, YouTube provider of choice has new videos. That's not how it works. Right? This is not true, right? I can have a variable, I can put it in a registry even if it's shared. There's nothing preventing that. And the answer here is actually going to be D, right? So it's a new wrinkle, but it's one you can manage, right? So if you have something pushed into a register during the time that is in that register, it will not see updates, right? Why do I bother sort of mentioning this? It's a useful aside. How many people pay attention to the compiler flags you're using when you're compiling programs? Again, I remember asking this 6 weeks ago, and only like 3 of you had ever compiled a program, but so it will turn out there's a fun way that you can have a non-working program appear to work. So if you compile with -O0 and turn optimizations completely off, it doesn't promote variables to registers. And so everything will be updated and shared in the memory system. And you'll be like, oh yeah, I can read and write all these variables, share them across a multi-threaded program. Then you turn the optimizations on, you wonder why all of a sudden all of your threads wandered off and weren't talking to each other. So this is a real thing that can actually happen. FYI, be aware. Make sure that the system actually understands whether or not something is shared or not. Okay. All right, so based on what I've just told you so far, very little, what I've told you so far about coherence and consistency. If our coherence issues here are that we have these multiple caches and we want to agree on values. If I don't have any caches, I don't have to worry about coherence or consistency. If only that were the case. No, not true. I still have to worry about coherence with no caches. Actually, also not true. If I only have memory, then there's only one copy. If there's only one copy, I don't have to worry about disagreement on what the value of the one copy is. So, no, that's not true. That also means that this is not true. We'll go back to B, where getting rid of caches fixes your coherence problem. Still, consistency can be an issue. And consistency is about the ordering among multiple accesses. I can have consistency problems even in the absence of caches if, for instance, I do not have ordered delivery of messages to my memory system. Right? My reads and writes could get reordered. Okay. Just again, all I want you to take away from here is that coherence is not consistency. And yes, if I got rid of my caches, I wouldn't have to worry about coherence anymore, but also I wouldn't have to worry about having any performance. So there we go. Okay. So let's talk about how to actually keep things coherent, right? It's what you're going to usually want to do. We will actually see some cases where we don't bother. GPUs, for instance, have some incoherent memories, but they also have coherent memories as well. GPUs are fun. So there's going to be some hardware mechanism that is going to enforce some necessary properties. And the way that we're going to start off here, we're going to start off with a technique that will work in the small. It will not scale. We can talk about briefly how you would scale it, but we're not going into the details on more scalable techniques. it will be enough to understand this in the simple case, and everything else is a performance optimization in the large. So let's just have a common point in the system that is observable, i.e., let's have a bus. All right, let's have a pile of wires that everyone can be listening to. So they will see all of the traffic that is placed on the system for interactions with the coherence protocol, some sort of broadcast medium. Okay. So what you can do then is you can implement your protocol on top of transactions on the bus for requests for upgrades, requests for data you don't have, operations on data that they do have. And we're going to mostly look at write invalidate protocols. There is another class of protocols called write update protocols. They tend to be very bandwidth inefficient. There are some very particular cases where they might be useful, but not on the types of architectures we're actually seeing today. Right, so we will, even though there are other protocols, we're going to restrict ourselves to write and validate. So how are write and validate protocols going to work? Well, again, think back to slide 9. Think about when things went wrong. X was 0. For 1 loaded a copy of X, which was 0. For 2 loaded a copy of X, which was also 0. All the copies are 0. Everyone can agree that the value is 0. As long as I'm doing a bunch of reads, I can have as many copies as I want. Right? No one is going to get in a disagreement about value unless the value changes. Right? So read sharing is fine, right? But as soon as I write the value, I might have some incoherence. So one way to ensure that I do not have incoherence of the value is to couple the update of one copy with the invalidation of all others, right? So every time that you are actually going to write a value, or at least get the permission to write that value, I'll get that in a second, you are going to ensure that no other readable or writable copies of an item exist in anyone else's cache, which makes it, again, equivalent to the degenerate case where only one copy exists in one cache and there is no longer a coherence problem. Yes, you do have to eventually update the main memory, but that's we were already dealing with write back. Okay. Now, if 2 processors attempt to write at the same time, what's going to happen? We're going to arbitrate. One of them is going to win and go first. Right? There isn't a well-defined ordering on what's going to happen. Right? 2 things show up at the bus in the same cycle. Some random decision is going to be made. One of them is going to go first and validate the other. The other one's going to wait, and then eventually it's going to do its right. There's going to be serialization. Right? So in particular, the coherence protocol doesn't care what the ordering is, just that there is an ordering. Right? So if A and B writes from core 1, writes from core 2 to set X to 1 to set X to 3, show up in the same bus at the same time. As long as they are ordered and everyone can agree on what that order was, whether it was 1 then 3 or 3 then 1, both of those are equally valid. Right? But there has to be global agreement. Okay. So here, basically logically, is a new piece of hardware. My core, whatever number of, I would call them private caches, are sitting here. And there is a cache controller that is snooping the bus. Right? Now, depending on your protocol, what you can look at is the amount of traffic that has to occur on this bus. Right? This bus is a physical object. It is large. It is a bunch of wires. Right? Sending messages on wires is slow and energy intensive. Right? So if you're looking at preferential properties of cache coherence protocols relative to each other, you might want to limit the amount of bus traffic. This is one of the metrics that you would cross-compare protocols on. Right? Is there a way to talk less on the big, expensive medium? Right? The other one, obviously, would be to change the hit rate of the cache because these write and validate protocol does cause things in your cache to become invalid. Those are sort of the 2 properties you're going to be thinking about. The right way to think about what is then going to be happening is what are the events of interest, right? So I can have a load or a store to my local data cache, right? So if I'm loading something from my own cache and it's valid, I don't need to tell anybody about it, right? Nobody else's problem. I'm not going to talk on the bus to do a load to something that's a hit, right? Certainly not. I mean, this is slow. This is distant. This is energy expensive. Load that's a hit should be my common case, right? If not, again, either my program or my processor is poorly designed. Right? So I'm not going to tell anyone about that. I have a local load, that's fine. I have a local store. We'll see that in a second. There are actually a couple of cases, depending on if I actually have write permission. Right? We have different notions there. That's going to get differentiated. But if I have a load miss or a load store, clearly, I have to go out to the rest of the memory system to get the data. Right? So all of my misses are going to be visible. And if everyone is snooping, then all of my misses are visible to everyone else. Okay. Similarly, all of my writebacks, right, our bus transactions will also be visible to everyone else. Okay. So locally, load, store, writeback. Remote, someone else's load miss, someone else's store miss. These are the things that the cache controller is going to be aware of and can potentially interact with the bus. Okay. So let's walk through what happens in a variety of protocols. Let's start with the simplest one. We've got two states, right? Does not get much simpler than this. The valid-invalid coherence protocol, sometimes also known as the modified or modifiable invalid protocol. Okay. I occasionally joke that it should be called the Highlander protocol because there can only be one valid copy. Okay, so every cache line you have is either going to be invalid or valid. From the coherence protocol perspective, right? So you can think of this is in addition to the sort of native bits of your state tracking in your cache. There's going to be additional metadata. In this case, this can sort of combine with the existing validity data. You don't need more bits. As we move on to larger protocols, you'll need a few extra bits, right? MESI is somewhat orthogonal to some of the other properties that you may have in your cache. Okay, and you can look at the transition arcs are based on the either local or remote observed elements on that bus. So if I have a line and it is in the valid state and I do a load or a store, I do nothing. Because the way this protocol is going to work is I know that I have the only copy of this line in any of the caches. So clearly I can read and write to it just fine. If it's the only copy, I can update it. No, I don't need any permission to do so. I don't need to invalidate everything. Everything is great. Right. Now, if anyone else wants this data, so think back to our example. I do my load into core 0. It's initially here in the valid state, right? And so I do a load, right? That's going to locally be a load. Externally, it's going to be a load miss, but nobody else has it either, so that's nothing interesting going to happen. And then I'm going to get the data from memory, set it to valid. Great. Later then, core 2 says, oh, I'd like to access X. I'm going to do a load. So it's going to do this transition locally. What's going to be happening at core 1? Because there's one of these state machines for every core. Right? So at core 1, it's going to observe that load miss from core 2 on the bus. Right? It's going to be snooping. So core 2 puts that data out, says, oh, I'm looking for this data. Anybody got it? And so I'm going to have to check on anyone else's miss whether I have that data, right? So if you look at what the job of this is doing, this is actually going to be checking for the presence of data for addresses that are coming across this bus, right? So you're going to be increasing the number of tag checks that are occurring in your cache based on other people's traffic. You can see where this is a scalability issue. If I have many cores on the bus, they're all asking for data, most of which I probably don't have. right? But I got to check anyway for the enforcing the coherence protocol, right? There are eventually going to be some scalability issues here, right? But for the moment, let's say we've got 2 cores. Everything scales to 2, right? Even satisfiability problems scale to 2, right? 2 sets polynomial, 3 sets NP card. So what I'm going to do is say, I have a copy, but there can only be 1 valid copy. So I'm going to invalidate myself and send data on the bus. Whatever my current version is the most up-to-date version in the machine, because I have the only valid copy in any cache. I'm going to send that on the bus, and the requester is then going to basically get that data served from me. The core 2's load after, right? So again, let's look at the sequence, right? So core 1, load X, right? Sometime later, core 2, load X, right? That data is actually going to be transferred on the bus from core 1 to core 2. We're not going to get it from memory, right? We're going to do that because we're going to check that we actually have the data, right? And then we're going to invalidate our own copy and send the most up-to-date copy to whoever requested it. Okay, so write invalidation. I got invalidated, my copy here. So initially invalid. But again, initially invalid. Now valid here. So pretty straightforward, right? So if you get evicted, again, if your own copy is dirty, you can write it back. The write backs will set you to invalid as well, just for here completeness. All right. This is a very, very simple protocol, but it has some obvious challenges with the way that you might want to actually use data, right? This is sufficient, right? This will enforce coherence, right? You have the valid and invalid protocol. You ensure that there's no more than 1 copy of a line in cache, and you will have correctness. What you won't have is performance for the common case, right? Because again, these are both loads. If both of these had copies, nothing actually would have gone wrong yet. This is overly conservative, right? This is a sufficient but not necessary condition. Isn't it? Okay. You can modify this to an update protocol. I'm just gonna skip it. Update protocols are push-based rather than pull-based. Again, only really interesting if you're looking at like speculative multi-threading or something like that. Okay, so here's another way of representing that same state machine, right? This may be clearer to some folks. So, right, here's your interaction based on your current state, right? You're in current state invalid. From this core, you receive a load or store, right? This is a miss. You go to V, miss, you go to V, right? If you are in the invalid state and you see a load miss or a store miss from another core, I don't care. I don't have a copy of this line, but I had to check anyway. This is still work done. There's no action taken, right? So there's a scalability cost, right? I have the line and it's valid. I have full permissions, hit. If someone else wants it, I need to invalidate myself and send the data, right? Okay. Any questions on the simplest coherence protocol? All right, we're just going to ensure that there is only 1 valid copy of any cache line anywhere in the system. So this is for every cache line, right? We can have a coherent state, right? Coherent state is either valid for coherence or invalid. And this is how we transition it based on bus transactions that we are observing globally. Watch it pictorially, right? Load X, got a copy from memory, X is 0. Load X. This is a load miss. The load miss is seen on the bus. So we're going to invalidate that, right? And get our own copies sent across the bus. I stored X. I don't have a valid copy of X. So I'm going to invalidate this copy, get the 0, then write 1 to it. Right. Now, again, why do I need to do that? We'll have a slide on false sharing in a second. But recall that the unit of storage and transfer between caches is not variables, it is cache lines. Right. So I don't know what has happened to this cache line in this other core while this is invalid. Right. That could have been modified. Other data that's in the same cache line, X itself could have been modified. So even if I'm just doing a store, I do actually need to get the up-to-date valid copy of that line here before I store into it. Right. Again, there could be multiple variables sitting in one line. Right. You need to update all the bytes. We'll show you examples of that later. Okay, we're loading from X. You can see obviously the performance this is garbage, but that's okay. It's correct, right? So at this point, when we also note that the shared memory system itself is also sitting on the bus, so it's going to observe the fact that X actually got updated. It'll keep itself up to date. And it'll just ping pong back and forth between them, right? But at least everyone can agree on what the value of X is. So a whole bunch of bus traffic, but correctness is there, okay? So there are some details that I'm not going to overly stress in terms of how to figure out whether you should be getting it from memory or from a particular core. It will be fairly obvious in the protocol, right? So I'll stress it how you connect it from the protocol, but I won't stress it in terms of how you're going to build the hardware to do it. Right? That's a little bit secondary. Right? But suffice it to say, your memory is effectively a first among equals peer in this coherence protocol, where it notices if nobody else says anything, then it's responsible for sending the data, right? Because it is the provider of last resort. Right. Okay, now let's start making this a little bit better. Right? And again, to understand whether or not this is better, you need to assume some things about how your program probably works. Right? So we're going to transition from the valid invalid two-state protocol to a three-state protocol, modified, shared, or invalid. Right? Because it may turn out that you actually want to have read sharing, because read sharing is fine. Right? Let's say that there is a common input file, and then you are doing a different series of computations based on that common input file. If that input file is read-only, you can all have your own copy. I don't need to keep invalidating your copy just because I loaded something from some read-only data. Right? This is a behavior I would like to support. Right? It will turn out to be really common. So, since we know that read-only sharing is fine, and it's just the updates that are problematic, let's specialize. Okay? So we're going to have a state that is invalid. We're going to have a state that is read-only shared, and a state that is modifiable. We're going to split this valid state into the M and S states based on whether or not, right, it is actually being written. Okay? And this is going to, in this particular example we saw so far, not do too much, right? Because they were actually reading and writing the same variable, right? But for the case where you do actually have shared data structures, right? Or even if you have shared data structures and you are going to write them, it is frequently the case that you are not writing all of them, right? Imagine I have a B+ tree in my database, right? I am making one modification to one record in my entire B+ tree, but I am traversing all these indices to get there, right? Everyone else can be traversing those same indices, which they are not modifying. Only the record itself at the end that is being modified is going to have cache invalidation, right? All the common shared structures can be shared just fine. Okay, so it's the same setup. We got one new piece here, right? So in the VI protocol, if I had it, I knew I was the only copy in the machine, so I had all rights and privileges to it. That is no longer the case here, right? What do I know about the number of copies of a line if I am in the S state? I know that there might be other shared copies. Right? I don't know if there are or are not. Right? This doesn't differentiate. Right? There's no counter. Right? But I know that it's possible that other people have copies of this line, so I can't just go and write to it. That would cause incoherence. So I need to transition myself to the modifiable state where I know that I have write privileges. I may actually move this out of an assumption of read-only into an assumption of read-write. And that's going to require a different sort of miss, a new type of bus message, an upgrade miss. Congratulations, we now have more misses in our cache system from the coherence protocol itself. Okay. So if we got 3 states, we need 2 bits. So now we're actually going to have to adjust the metadata per cache line. Again, every cache line in the system will have a coherent state. Right? So this is, along with your tag, your dirty, your valid, right? Your valid is now going to sort of be replaced by this modified shared invalid. Right? You can overlap the invalidity of your coherence protocol and your sort of initial state of your cache, but or you can just have both. Up to you. Okay, so let's again walk through the table. Right? So if I'm in the invalid state and someone else has load misses and upgrade misses, I don't care. I have to check that I am in fact in the invalid state to know that I don't care. Again, scalability, but no action needs to be taken, right? I am basically a non-participant if I do not have a copy of this cache line from the perspective of dealing with other people's messages. If I am in the modified state, I have the maximum number of privileges. So reads and writes are just hits, right? If someone else wants to read the data, I am going to downgrade myself to shared, send a copy of that data, right? And then there will be 2 copies, both in a read-only privileged state, and the memory will be updated at the same time, right? We'll write this back to memory as well. Right? So at the end of a load miss from a remote core to a core that has it in the modified state, we're all going to end up in S, and memory will be updated with the most current value. So we'll basically reset it to a read-only mutually visible state. Okay. If someone else is writing, right, either they're requesting write privilege with an upgrade miss, or they are performing a store miss. They didn't have the data at all. In either of those 2 cases, I will, in the modified state, well, actually, in the modified state, it can't be an upgrade miss. But in the modified state, there'll be a store miss. I will send the data and validate myself. So it looks pretty similar. All right, let's walk through what happens in shared. Okay. So in shared, if I have a read, great, I get a hit. I have permission to read this line in its shared state. If I try to do a store to it, I do not have permission to store to my own local copy. I need to get agreement on how many copies there are before I can do this. So I'm going to put an upgrade miss onto the bus, wait for that to resolve, move myself to the modified state, right? And then proceed to actually get my store hit. Okay. If there is a load miss from another core, I don't have to do anything, right? I have a copy. I could send it. I don't need to. There's not really a notion of ownership here other than with the main memory. I'm going to sit here and wait for memory to take care of this. I'm like, yeah, not my problem. Memory will figure it out. Whatever copies in memory is the same as mine. We're all in a shared read-only state. You can get it from anybody, so you can get it from memory. Not my problem. Right? Again, this is a scalability issue. If we don't have a notion of ownership, and they all tried to respond with okay, don't know what happened there. If they all tried to play nice. If they all tried to respond with the same data at the same time, you'd see that wouldn't really make a lot of sense. So the protocol decision is memory will take care of it. That way you default to one entry that will respond, makes your life a little simpler. Okay, if someone else is trying to write it and I've got a shared copy, I am going to just invalidate myself. I don't need to send anything. Again, right? I don't have the sort of, definitive copy of this. I just have one of these shared copies. It's not my responsibility to make sure they get the up-to-date version. Memory will do that if it was a store miss. And if it's an upgrade miss, they already have the up-to-date version. Right? I just need to invalidate myself. My version is no longer valid. Okay. Any questions about how this allows you to have coherence on read-only data, but still preserves the writing properties? Right. How many people have seen reader-writer locks? 3 of you? Okay. So some similar ideas, right? I can have as many readers as I want, only one writer at a time. Similar properties are at play here, right? So the same general idea about synchronization, about agreement on value ordering, serialization in parallel and concurrent processes shows up, whether it's distributed systems, operating systems, cache systems. Some of these concepts are just, fairly deep in how things just work. Okay, so the same thing in practice. Again, this particular pattern, not that interesting, but I load X, so far so good. The 0 in the shared state. I load X. Load miss, so this is just gonna go, not my problem. It'll get it from memory. Now we got 2 of them. They all stay 0. This is consistent and coherent, and everything's happy. There are no writes. Right now, as soon as we start storing, even though I have the data, it is the most up-to-date copy of the data, I don't have permission to write to it, so I have an upgrade miss. I have a bus transaction to figure out that I have permission to write to the data that I already have. Not ideal, but again, sufficient. So that upgrade miss is going to be seen by core 2. It's going to have to invalidate itself. All right. So the state of the system after this upgrade miss is going to look like that. Okay, again, this 1 has not been written onto the bus yet, so memory doesn't see it. Right. Now when we have a load miss, bloop, we will actually get it from here to there. Given the time remaining, I'll go over MESI later. So let me flip back to programming models. So what I mostly want to talk about is the fact that all of the programming models that you are used to, again, there's some esoteric ones out there, but if you're using programming models for things that look like what you think of as a processor that you would go and buy as a computer, they all assume coherence. Right? So all of these models are built on top of assumptions that you actually have a coherent memory system. Right? They will not work if you are running them on hardware that does not have this property. Right? So pthread, if you do not actually have shared physical memory, does not work. Right? OpenMP, if you do not have coherent shared physical memory, does not work. The Java thread support, if you do not have shared physical memory, does not work, etc. Right? So, but there are a bunch of language or library level ways of expressing that your program can be parallel, right? And they're going to leverage all these underlying pieces to actually make these things work. Now, the model that all of these are going to be executing on in terms of how your program works will actually turn out to have a lot to do with your consistency model about what is legal, right? Because again, they all just assume coherence is there. right? They don't have any disagreement about that. That's just sort of a given. They don't even think about it. But the order in which things happen is very interesting, right? So a lot of the models we have for multi-threading were actually developed at a time when you had multiple sequencers of execution, but only one actual physical core, right? So on your mainframe machine of the 1970s, right, you had preemptive multi-threading where the operating system would run you for a bit, then run some other thread, then run some other thread, then run some other thread, then run some other thread. And so a lot of the models about what a correct concurrent, again, concurrent and parallel, not actually the same thing, what a correct concurrent execution model would be is that it would be equivalent to some interleaving of the execution of the instructions of your various threads, right? And that would get you actually something called sequential consistency. It will turn out that when you want to actually run things on parallel hardware, concurrent programs on parallel hardware, enforcing sequential consistency is actually expensive. And as I said, we'll get back to consistency in the back half of this slide deck. Real processors actually have somewhat weaker consistency models. Things like total store order is weaker than sequential consistency. Or if you're ARM, release consistency. We just gave up. No, I'm joking a little bit. There's more to it than that, but it's very loose. So how many of you have ever noticed that OpenMP is natively supported by C++ and C since like GCC 4.9? No one here has ever, anyone here ever made an OpenMP program? No? Okay. So even languages that were designed for basically serial execution, right? The age shows, have had extensions to them through pragmas that allow for certain restricted cases of parallelism to be easy. Right? So if I want a parallel for loop, right? For I equals, 0 to a million, carve it up into 8 parallel chunks, right? I can do that with like 2 lines of pragma and linking against OpenMP. Right? It'll handle all the multi-threading for you for things like a parallel for, or for a fork join model. If I want to do arbitrarily, complicated asymmetric pipeline parallelism, no, go roll your own P threads. You got to sort of build that stuff up from the ground up. If you're looking at newer languages, I mean, yes, Java is an old language, but it's newer compared to C. Those have language synchronization primitives built in at the language level, right? Java has a notion of mutual exclusion at the language level. It's not a library call. It's not some sort of, retrofit, right? It's just part of the language. How many people have used Rust or Go? Okay, couple. Those have communication channels, right? Those have asynchronous FIFOs at the language level. I can basically just say, send message to other communicating thing, right? It's native. Yeah. Python threading model is, let's just not talk about it. It's not amazing. Now, fun fact, Java's current memory model actually is not its first one. Turned out that there were actually some problems with the first proposed Java memory model and had to be revamped. Again, if you're writing serial code, no one would have noticed, but there were some weird things it was doing in parallel code that had to actually be fixed at some point. So I say this to note that getting the abstractions right is not easy. And while I would like you to be aware of how people build multi-threaded programs, and it would be great if we all spent more of our time writing parallel and concurrent software, it does appear to be fundamentally just harder. And that's not going to be the focus of what we're going to dwell on. We're going to look at a very, very limited set of the ways that you might interact, like locks, barriers, and call it a day. There are a large number of potential synchronization primitives. We're not going to do more than a couple of them. But I'll give you at least a flavor of how hardware can actually support what software wants it to do, right? So again, the right way to think about this is that there's some things that hardware just has to solve, like, can I give you an agreement on what a value of memory is? And there are other things where, while you could build hardware for it, it's really more a question of understanding how software wants to exploit your parallel machines, right? So the advances in hardware, I mean, the biggest recent advance in hardware support for concurrency, anyone want to take a guess? About 10 years old. Transactional memory support. It came in with Haswell in 2012. The ability to do optimistic concurrency where if there were some disagreements, you just abort it and pretend that the transaction never happened. With all sorts of restrictions that everything has to fit in your L1 and right. So those things are come in occasionally, and they're they're fairly modest. You're going to build more interesting things on top of them. We're not going to see direct hardware support for incredibly complicated things. Instead, what you're going to get is primitives that allow you to do the particular form of communication that you want to actually perform. Okay, so we'll pick up with MESI, the last of our 3 coherence protocols that we're going to cover. We'll pick that up on Tuesday.